why and how to use simulation. And perhaps a less elegant title is why bother with it. It's what I'd like to talk a little bit about today in the next 20-25 minutes. So to start off, I'm a big believer in giving sort of context for talk. So first of all, I'm going to be speaking to you. Who are we? Who is Maplesoft and what do we do? I want to go through that pretty quickly, then talk about why I think you should care about this. And if I convince you that you should care, how it works. And a question that we often get is how much effort is it to actually do it? At the very end, I'm going to be going through some use cases of how our customers are using it to solve their problems. All right, very quickly, who are we? We are Maplesoft, over 4 decades in engineering computation. We started from a small startup at the University of Waterloo, and now we're a global company. Our software is in universities and companies all over the world. We have a variety of products, but the one that I'm going to be talking about today is at the bottom of this slide. It's MapleSim. It's a system-level modeling tool. I'll talk a little bit more about what I mean by that. And it's got a specific toolbox that helps you model and get information about web handling or roll-to-roll systems. So, system-level modeling. What do we do? The big thing that we do, and this I talk about this as my ugly slide because it is kind of ugly, but it's very simple. We do 2 key things for our customers. One, we help them design better machines, and we help them solve complicated operational or control problems that they're facing. And the main way that we do that is through tools, our software, and services, our application engineering team, working with customers for modeling and simulation. Now, simulation can mean a lot of different things. So let's maybe pause briefly to talk about when I'm speaking about simulation and in the context of MapleSim, where it fits in. So imagine I've got a little picture of a line there, but imagine that's like the scope from a detailed part all the way on the left there for detailed scope to a whole factory and the broad scope. So we look at the broad scope, you've started getting the smart factory stuff. And when people talk about simulation they're often, the things they're concerned about are moving things from, machine to machine to machine down the line. So they're looking at the eyes, are they picking up the product moving so the gate opens at the right time? When the web is cut, is the machine or the robot that takes that and moves that roll somewhere else to move on, is that all that timing working and being in place? They're looking sort of at discrete events, not at continuous dynamics, is what I would say in the simulation world. Moving along to more detailed and a slightly less scope, now we're looking at a machine or we're looking at a web line, or potentially even a portion of a web line. You can snip it and just look at the part that you're interested in. But the kinds of questions we're asking now change. We're asking questions about things like tension or motor torques. What's involved in the control to actually start this up and adjust the dancer position, for instance. These kinds of things are now the questions you ask of a system level model. And then just for completeness, we can add on the detailed scope, and that's when we're looking at parts. So often people talk about, what is the actual deflection of this or the twist in these kinds of parts. And that's a more detailed scope. You could theoretically use FEA to model a much larger portion of the system, but the time and effort involved usually doesn't make it worthwhile. So now you get an idea that, I say system level modeling, this would be an example of a system level modeling tool, representation of a web line. So you've got blocks that you drag in, you connect them up, and you can run the simulation. So that's my system level modeling picture. But of course, you're not just limited to blocks in the web handling world. We have blocks from all domains. So you can grab from hydraulics or pneumatics or magnetic. And one of the cool things about system level simulation is that you can sort of see what happens at the boundaries of these domains as they interact with one another. And so you can drag them on and run simulations and get information about what happens with these different interconnections. Today, as was suggested in the title, I'm going to be focusing on web handling and roll-to-roll systems. Okay, so here's a brief snapshot of our web handling library. Again, you can see a model on the left there drawn out. I've got a snapshot of some of the components there on the right-hand side. This library is constantly being updated. Just last month, we added components for air entrainment so that you can model those phenomena in your roll-to-roll systems as well. But there's all kinds of problems and types of things that you can add in and take a look at. I've listed a few here. I've shown a snapshot of the model gallery if you want to go online and find sort of more examples from us. But we'll talk more about these in a little bit more detail. I just want to give you an overview of sort of what it is we do in the web handling world and what kind of things that you could imagine we're modeling. So let's get to what is quite likely the more important question, and that is, why should you care about this? So, I think the best way to do it is let's have a discussion about what the problem solving looks like for an engineering team. So they're there and they get told, hey, we've got a new design. Now it might be a new design that they have no familiarity with, or it's a new type of product that they want to get into. And so you want them to sort of start coming up with ideas for how are you going to build this new machine and this new sort of roll-to-roll process. Sometimes, and I mentioned it previously, new materials come into play. So you've got a machine already, but it was designed for a different purpose, a different material. Maybe government regulations have come in and said it has to be thinner, or it's got to be some material that is more easily recycled. And so you've got to change your system of a current machine to fit a new set of criteria that you're working towards. Often, you've got a machine that's out there that's now starting to show some quality issues. Maybe you've got some tearing happening or some wrinklings going on, and you want to track down what's going on there and get that problem solved. And if you have no quality issues, it's a design you know about, everything's running well, there is someone who's going to say, I want it to run faster. And at that point, you will probably start running into quality issues as you turn the speed of that machine up. So how do these problems get solved? These things come up, the engineering team gets faced with them. What do you do? Well, the engineering team is clever. They come up with solutions, right? They come up with an idea of how they could solve this problem. And they say, okay, here's where I think we should, maybe if we increase the wrap angles, we're going to move these rollers. Great, we'll try that out. So they pass that along, you get technicians coming along, they start doing work and move along. Maybe you build a prototype machine and you start moving things around on that machine and you test it out. Now, if you're lucky, the technicians will record data coming out of the machine. You can analyze that data and say, hey, does it solve our problem? And if you're lucky, maybe you only have 1 or 2 passes through this. But often you get this back and you just keep doing this process. And we've come alongside customers who've had a sticking issue for months. And they've come along and said, we're just having a hard time getting to the bottom of this. And part of the issue is just the time it takes and the cost involved for each of those loops. So let's look a little bit at those challenges, right? First of all, the engineers often are working without a full set of information. There are never enough load cells or sensors on a machine for them to always get a clear picture of what's going on inside that system. I mean, sometimes load cells are expensive, sure. They're sometimes just, you have to maintain and calibrate them. And sometimes you just can't even fit them in the right spot that you need them for where you want to be analyzing the system. So first thing, engineers don't necessarily have a full picture of what's going on. The second one is that every time you do one of these tests, it costs money. Now, some areas running the material is not that expensive, it's not a big deal. But in some areas, particularly battery, you have pretty expensive materials, and you guys can calculate on your side what it costs to run each one of these tests and sort of throw away that material each time. And even if your material isn't expensive, there's people's time. You've got your engineers looking at this problem. They could be looking at other things, but they're focused on this. You've got technicians involved who are updating the machine, who are pulling the analysis results to give to the engineer. Like, you've got a whole process going there that costs time and money. And then the last piece there, of course, if you don't have a prototype machine and you're working on something that's actually in production, there's costs associated with downtime. So if you want to ask the question, why bother with simulation? I mean, the ideal goal of simulation is that it can kind of replace itself in that loop. You can come up with that idea, you go to implement it, well, you're implementing it in the software where it's quick to do, and then you can do that iteration faster, right? And because it's software, we don't have to worry about load cells because we have all the information. You can see the tension in every span. You can see what the wrap angle is as that dancer moves. You have all the information for your engineers to make decisions. Obviously, you're not generating any material waste because it's a virtual machine, and the timing to do this is much quicker. It's very fast to take a roller and move it and try out the simulation again and see how that changes your results. And then finally, obviously, you don't have issues with production because that isn't the machine in production, it's the virtual machine. Now, I'd love to tell you that that is the picture and that's what simulation does, but it's not exactly like that. Probably a fair view of a loop is what you see here. So you're presented with the problem, the virtual tests are happening, so you're looping on that and you're solving it and getting an idea, but you're doing those in fast iterations, right? You can test things out quickly. Once there's something that you feel satisfied with, then you can take that and put it in and do a physical test, which is the sort of more expensive and costly loop. But now you've gone through a bunch of iterations. And the other thing I like to talk to people about for that is that very often it means that you've actually optimized in the virtual testing environment where you've said, this is the best solution. As opposed to when you've got a slow loop, you choose what I would say is a satisficing solution, the first one that satisfies the problem, because it's expensive to keep trying more things, and everybody is always pressed for time. Okay, I hope that is at least a little bit compelling to you to hang on for the next 10 minutes of this. But I want to talk now about how it works. So first thing you have to do, obviously, is build a basic model. I mentioned earlier you can do a whole web line, but you can also do a part of a web line. So I've got a very simple system here, 2 rollers and a dancer. I'm assuming I'm cutting this, and I'm just going to look at what's going on in the dynamics of this portion. So the way that you would build this in MapleSim is you'd first say, okay, I've cut it. What are the tensions and velocity going in and the tension coming out? I'm going to take those. Now I've got my area or my region that I'm analyzing. Next, I'm going to add rollers for every single one of the rollers that I see in my sketch. Like you can see here, these would be the components that I'd be adding in, and I'd make sure I've got the web going on the right side. Don't worry, the machine or MapleSim will automatically calculate those spans and wrap angles. So we drag in the spans so that those can get automatically calculated. We then have to say, where are these in the XY plane so that we position those rollers so that we say, here's where the rollers are located. And then this last one, obviously, the dancer isn't fixed. It pivots about a point. So we put a pin joint in, or a revolute, it's sometimes called, and we attach those in with the correct offsets. And that's our web line. So you can see the web line there, and you can see the 1D blocks that we use to build it. Now, MapleSim will give you a 3D representation of this. We allow you to have Z offsets in your model, and we can give you an idea of what your web will look like and how the tension will propagate through it. So that gives you an idea how to build the physical system. But of course, we know that that is a controlled system. So let's look at this model here. Let's say that I've got this unwind drum, I've got a rotational dancer, a nip roller here, and I've got a load sensor. So I want to add some control to this. And I'm going to use this as my master drive, position control on the unwind, and then attention control based on that load cell. How do I do that? Because that's part of my analysis that I'm taking a look at. And I've got at the bottom here, this is what your 1D, this is what your block diagram looks like with question marks around the control. Well, last year we added a library to actually allow you to add control directly into your model. So you don't have to leave the software, you can stay inside of it and very quickly test different type of control ideas right there. Tension control, position control. If you need, we can add motor dynamics or approximate them to second order. Just so that you can have this playground, if you will, for trying out new ideas or for trying to understand the phenomena that you're seeing in a model. Now, if you feel more comfortable, our tool can also hook directly to the PLC. We can talk via the Ethernet IP protocol and talk directly to a machine, a PLC, and get that information. And now our model will act as the virtual model that the PLC is talking to. You don't have to hook it up to the real prototype. You can hook it up to the virtual. We also have the ability, some tools allow you to import functional mockup interfaces. It's just a way of wrapping a model, and you can load it directly into your PLC code. So I think I've said what we do, why it should be important. what it looks like, the next big question people have is how much effort is the model? And what they really mean by this is, can I get value out of it, right? Because if it's too much work and too long and I get too little value, I get too little information back, it's not worth the effort and time. So let's talk nuts and bolts about what's required to make that model. So the first thing you've got to do is you've got to gather your inputs, right? There's the size and location of your rollers, your nip rollers, your unwind wind drums, those kinds of things. So where are they located and what are the diameters? Need that information. Web material properties have to come. Sometimes people have an idea of the nominal values for this. There are tests you can do to test for, the elasticity of that material, but you can put a nominal value in to start. Your drag, your coefficient of friction, and inertia. These are sometimes less known. Inertia, we can approximate based on the material, or if you know if it's a hollow roller or not. That's pretty straightforward. Roller drag often is negligible, but it's useful when you're trying to reproduce something you see somewhere. So for a nominal model, meaning a model with not tied to a specific machine, but a model that is a general representation, we can put in a nominal value there and also that coefficient of friction. We've talked about the actuation and control elements, and then I say special blocks because the converting, the chemical process that might be going on during your converting or such, we don't model that internally. And if it changes, let's say the web properties, we wouldn't predict it, but you can enter in what the resulting web properties are inside of MapleSim. So if you grab those things and put them together, you can construct a nominal model. How much effort does that take? Honestly, the big piece of time is getting the information that you see on the left there. If you have that information, or at least the basic values of it, building the model is a day, 2 days, faster if you're an expert with the tool. So the building of the model is often the smaller part. It's getting the information. When I go and I give this presentation other places, people often laugh at this and just kind of nod because they're like, yeah, tracking down what their roller pieces are sometimes is a big part of it. So the question is, okay, I've done the work to get this model. Building the model, the software side of it actually isn't that large. What can you do with these nominal models? Well, actually, the answer is you can do quite a few things. First of all, you can start to immediately get a look of how the system works, like how the tension will propagate through that machine. I mentioned early on that often engineers have to work almost in the dark, right? They get one plot coming out from a load cell, and there's some vibration in the mechanism, and they're supposed to say where it's coming from. This can give you an idea of what's going on in your machine. You can obviously experiment not only with different control strategies, we talked about that, but different designs. What happens if I move a roller? How does that change the wrap angle? What happens if I add a dancer in this location? Can I control the tension better and get rid of some fluctuations? You can start to get a sense of how things will operate with different materials. We have customers they ship out machines, or they have machines on their side that they're constantly running new materials through, and they want to get an idea of how that machine will behave. This allows you to do some quick exploration with very little changes and sort of having to run on an actual machine. And then finally, there's the virtual commissioning side. Nobody likes it when a machine starts up and material goes flying off across the room. And so this gives you a chance to test out your control code directly against a virtual machine first. Just get another step of confidence of how that initial commissioning phase is going to go. Now you may say, I've got a model that's got a specific problem. I don't need a nominal model. I need something that maps to a specific asset. And so in this case, what do you have to do? How do you take that nominal model to an actual machine that you've got on your floor? Well, I'm highlighting the things here where we made some estimations, right? The web material properties, and particularly that coefficient of friction. Those two having to do further look at, how do we refine those? Well, the way that you do it, in this case, you have a machine, and that machine has some data that you can pull back from it. We have tools inside of MapleSim that allow you to take that information that's coming in and map it, or run the simulation model over and over again, adjusting those coefficients, friction, for instance, and the material properties until you match the results that you're seeing from the actual machine. Then you can start to feel confident that what you've got is a match to the asset and not just a general model anymore. And you can start doing experiments with it to try and say, hey, I'm seeing this in the model. What if I tweak my simulation model do I start to see those kinds of results? Do I start to see those types of errors that I'm seeing in my physical system? Okay, so then maybe you're like, wow, this is fantastic. Can everything be modeled? And this is obviously like a setup question, right? Because, I mean, the answer is we like to think that our software is super great, very clever, but no, you can't model everything in our software. And actually, sometimes there's phenomena that is new to us that we're like, hey, there is a way to model that. But in reality, it's not worth, when I say you can't model something, what I mean by that is that you can't model it with a reasonable return on investment. Like the amount of effort would be too much. So there are cases where modeling something to the 100% is not worth the return on investment. But does that mean that simulation is useless? I would argue strongly that it's not. It can still be very beneficial to give you insight into the problem so that the parts that you're trying to track down, you at least have more knowledge going into the parts that you're trying to trace. Often this comes up with converting, right? Maplesoft doesn't model the chemical interactions that are going on inside your converting process, but we can give you a good idea of what's going on with the tensions leading in and coming out of that, so that you can sort of make better ideas of what's going on inside. One of our application engineering team members had talked about this and actually had likened it to Sudoku, and I really like the example. For those of you who are maybe not familiar with it, it's where you have to make, like, all the columns have to be the numbers 1 through 9, all the rows are 1 through 9, and every box there has to include the numbers 1 through 9. And so much of solving these problems is sometimes you can say, oh, I know for sure this, and I know for sure this, just using logic. But very often, there's whole sets where you're like, oh, this could be a 4, but it could also be a 5. And you have to actually, you try one, you work it out, and you find it doesn't work, and you have to go back and you figure that out again. And it just takes time to sort of figure out what your estimations are. You can think of simulation for things that we can't model everything, kind of like filling in some of these squares in a Sudoku puzzle. It doesn't give you the whole puzzle, it doesn't solve and give you the whole picture, but it starts to fill out that picture and fill out some of those unknowns. And it rapidly can, test other unknowns that you'd like to experiment with. And this allows your engineers to focus on the things that are really potentially causing you the problem, be able to either remove or have a better understanding of the things sort of that simulation can represent. So let's talk a little bit about use cases. That's talk about nominal models in general and detailed models in general. Let's talk about some use cases that have come from our customers. I always like to preface this with the fact that these are any pictures you see here come from our training or internal or examples that we've got. These aren't our customer models. And they're ones that we've got that are closest to the spirit of the problem that our customers were talking about. The other thing you're going to notice as I go through these use cases, a lot of them have to do with pilots. And that's because often people want to get a sense of, can they use the technology and be successful with it? And once they have the tool, we don't talk about the, the projects that they're actually working on inside. So here we go, use case, a large print manufacturer from Europe. They had shipped a product or shipped a machine to a customer. The machine wasn't behaving. Eccentricity was thought, maybe based on the results coming back. They were able to use software to say, hey, this is the roller that's got the eccentricity mapping to the results that you're giving. And that kind of thing gave them confidence to say, hey, we can use this for other tasks. When we're looking at web lines, we can trust the results coming from the simulation. This is another one of those proof of concepts where there's a shuttle model. And they built this, they knew that it had particularly, it's sort of a more complicated use of WebLine. It's got some interesting tension dynamics that go on. They wanted to make sure they could reproduce those phenomena with the simulation model. We worked with them, they were able to reproduce it, and so now they've got the confidence they can use this for their new design and development of new machines. This is a similar kind of use case, although in this case we're talking about accumulators. And you'll remember I said you can chop a line and just take a look at a certain part of it. And that's what they were doing. They were looking at the buffering portion of the system and trying to find out if they could reproduce what they saw in their test machine. Obviously, obviously maybe because I'm showing it, they were able to reproduce it. But now they're using it to optimize their buffers, the number of rollers, the location, the materials that go into those rollers in the buffer. for their new designs. This is an interesting one because the problem a customer had been having with a given machine, and really the issue boiled down to the materials that were coming into that wine drum had different thicknesses, and these would cause abrupt changes to the radius of the wine, which meant that there would be tension changes and speed changes that would then propagate into the system. Simulation helped discover this, and then simulation provided a playground or a test bed to come up with solutions to remove those fluctuations or vibrations that they were getting as a result of these abrupt changes to the radius. And I should say, we actually didn't have a component in MapleSim to model this kind of phenomena until we had this discussion with the customer and working with them, and we subsequently built that in. And so now when you grab MapleSim, a component that allows these kinds of capabilities is available in the product. And that's how actually a lot of the new pieces coming into the tool, it comes from our work with customers and new phenomena we encounter as we're working with them. And this last one is slightly different. This is where a customer wanted to get into a new field they weren't familiar with, battery Z-fold battery construction. And so they used our tool to say, hey, let's try out some different designs. We can use it for motor sizing. And before we build something, we can have a good idea of a lot of the pieces of the puzzle. You remember that Sudoku puzzle? A lot of pieces of the puzzle before we actually start building this thing. Okay, so talked a lot. Quick wrap up. Why bother with simulation? Simulation allows you to do some fast iterations. When you're trying to solve a problem, it allows you to do things that allow you to get it allows you to quickly iterate on your problem without having to go through that slower and more expensive testing on the physical system. And really the big goal here is to give your engineers insight into the problem, because if they have insight and can see the big picture, not only can they build better machines, but they can get those products and solve problems faster. When I talk to people, they often have a common concern is, one, we don't have the experience to do this kind of thing. And that's fair. Maplesoft has an engineering services team that can give training or can work with you on the beginner projects so you can develop those skills. Maplesoft won't be able to model our system. There are cases, and we are happy to have that discussion with you as you look at it, where if you remember that Sudoku puzzle, sometimes it's true, simulation can only fill in a bottom corner, and we can agree and talk about whether or not that bottom corner gives your engineers enough extra information that it's worth the simulation. But oftentimes, as we talk about it, you realize there's enough of those squares being filled in that there's a lot of benefit to the simulation, even if the entire process can't be modeled. But don't worry, we'll be upfront with you. It's no good to us or good to you to apply a simulation, a system level simulation, to a problem that doesn't fit. And then the final thing people say is we don't have time to invest in this. And actually what that often really means is that we don't perceive that we will get enough value in it for the effort that we're putting, a value from it for the effort we put in. And again, this is a great opportunity to say, let's come alongside and do a proof of concept, a smaller model together that is a real problem. So it's actually helping you solve a real problem, but is narrowed in scope so you can get a feel for how this can work inside your organization. So at the beginning, I said my ugly slide, I'm going to show it again, but I hope it makes a little bit more sense when I say that we help our customers design better machines and solve complicated problems with tools and services. I hope you have a better idea of what that looks like in the context of MapleSim simulation. You've seen this webinar. There's obviously more information on the web that you can take a look at. I'll just pull these up quick. We've got stuff, obviously different languages. We have experts who go through how you could use simulation and connecting it directly to sort of touch and feel problems you see on your web line. Connected to all of that, we've got a conference coming up on June 4th. It's a mini conference. And if there's some pieces here that you found interesting, I'd encourage you to be more discussion, maybe more hands-on discussion of how you can use simulation to solve your problems, as well as sort of overviews of new things going on in the field and new products coming to the roll-to-roll community. With that, I am finished with the core of the presentation and open and available for questions that may have come up while I've been going through. Okay, so one question that came up here is, can MapleSim model other systems that might be part of converting, like fluid flow and a coating delivery system? So yeah, there was the one slide I showed earlier on. We do have different domains that you can bring in. Hydraulics is part of that. Fluid flow, we'd have to talk with you a little bit more about, because I'm suspicious that the piece you care about is sort of nozzle spray and maybe putting that along when you're doing your coating, how that works, and can we model that process? That actual spraying process isn't something that we do directly inside of MapleSim, but certainly chat with us. We can talk about what pieces we can show you and we can help you with, and what pieces that are sort of beyond the capabilities of our software. Yeah, a good question. We've been asked about that. Sorry. Can MapleSim simulate registration errors on printing process? We're actually, this is a topic somebody else has been looking or talking to us about, and we don't register errors, but we're looking into being able to track points on a web, so that you can take a look at how that point transfers and moves through your web line. The actual tracking of errors where you make that signal back to the PLC isn't something we do directly. But the phenomena of tracking points along a web is one that's actually actively being developed or looked at inside on the R&D side for Maplesoft right now. Can you detect when things like wrinkles or breakage will occur with the simulation, or is it just measuring tensions? Yeah, fair question. I would love to say that we can just tell you, and breakage occurred. That's not something that we do. We do measure tensions, and we do have tools that you can use for post-processing to take a look and say, what are the odds or the likelihoods of some of those things happening based on the tension and control measurements that you see coming back. But you can't directly see wrinkling happening in MapleSim simulation. Oh, I need to scroll down here. What procedure would you recommend to start to model an existing equipment, and how do you know that the model is good enough? That's a great question, actually. Knowing when a model is good enough. When have you modeled enough of the dynamics to make sure that you're capturing what you need? So let's break that down into two. So what procedure would you recommend to start to model an existing equipment? Well, the first point is you could model that line, get that nominal model sort of put up together. That's relatively quick to do. And now you can at least see sort of the behavior pieces, right? And then as you start looking at that, you can say, because of course in a simulation, you can start adjusting things and finding out what aspects of this machine are we most sensitive to? Like if I change the modulus elasticity, how much do my results change? If I move these rollers around, how much do my results change? And you get an idea for what are the important parts of your system. And when you find out the important parts, that can maybe lead you to, maybe we need to make sure we get that inertia correct, or we need to get those coefficients of friction correct. So you can use the model to tell you what the most important parts of the model are, sort of to go deeper on and to take a look. Sorry. Yeah, this is connected to one of the other questions or statements I said before. It's a question about, can you model different converting processes, and the converting process, often the chemical interaction kind of pieces like that, that's not something that we model on our side. What we do model on our side is, for instance, that chemical interaction may result in a change to the web material properties. You can have and inject new web material properties at another point in the line to see how that affects things. But the actual prediction of how those chemicals are going to affect the properties isn't something that we model. Can you extract output data into a CSV? Absolutely. Any of the data that you see, so you saw some fancy visualizations in my presentation where you had colors changing based on the magnitude of the tensions, or you saw the dancers moving. All of that information can be extracted into a CSV. If you want to do further analysis in Excel or some other tool, that's fine. Whatever your normal procedure is there, we can give you that information and export it for you.